Hello, sir. Have you joined? Hello. Sir, ଆପଣ join କଲେ sir? Hello. Hello. Sir, please switch on your camera, sir. Switch on your camera. Sir, ଆପଣଙ୍କର camera sir switch. Sir, କୁହନ୍ତୁ sir. Sir, ଆପଣଙ୍କ camera sir on କରିଛନ୍ତି? Sir, ମୁଁ ଆପଣଙ୍କୁ sir. ହଁ। ଆଚ୍ଛା ଅଫ୍ ଅଛି ବୋଲି କଣ କହୁଛନ୍ତି? ଏସସି ମିଶ୍ର ଗୋଟେ ଦେଖାଅ, ମାନେ ସୁରେଶ ମିଶ୍ର କରିଛ, ଏସସି ମିଶ୍ର କର, ଆଉ ଗୋଟେ କର। ଟିକେ ଥାନ୍ତୁ। ହଁ, ସେଇଟା ତ ମୁଁ କହୁଛି। ସାର୍, ଆପଣଙ୍କର କ୍ୟାମେରା ଆଉ ଏମଆଇସି ବୋଲି ଯୋଉ ଉପରେ ଅଛି ସେଟା ଫେଲ୍ ହେଇଛି କି ଅନ୍ କଲେ? ଗୋଟେ ଜାଗାରେ ହଁ ହଁ, ବାସ୍ ବାସ୍ ବାସ୍, ଏବେ ଆସିଲା।
Okay. Okay.
ହଁ।
Thank you.
ହଁ।
Okay.
खाली आपनकर कैमरा डाटा के फोकस पॉइंट रे रखंतु माने विजिबिलिटी बस now the visibility is okay apuni
Okay.
Okay.
Is it
Okay.
fine?
So welcome to all of you. We are 5 minutes late. I should be excused. As you know, there is little amount of technical difficulties every time. So we are very fortunate to have amongst us today Professor Dr. Suresh Chandra Mishra, and we all have assembled here for the 66th Shiksha and Anusandhan Fortnightly Academic Lecture, which is aptly known as SOAFAL. And this is the overall 66th SOAFAL oration or the 16th SOAFAL oration in the third SOAFAL series, whose annual theme is Integrated Maritime Studies. And today's the speaker is a very distinguished academician. He was the former director Indian Maritime University, Visakhapatnam, and also the professor in the Oceanographic Department of IIT Kharagpur. So I have the privilege of introducing him to the audience. Just a brief biodata. Dr. Suresh Chandra Mishra graduated with BTech honors in naval architecture from IIT Kharagpur in 1970 and obtained his PhD from the University of Newcastle upon Time, UK in 1976. After a brief stint as design engineer in Hindustan CPR Limited at Visakhapatnam, he joined IIT Kharagpur as faculty and retired as professor in 2013. From 2009 to 2013, he was the first director of Indian Maritime University, Visakhapatnam campus. After retirement, he has been a visiting faculty at IMU and of Hindustan Institute of Maritime Technology, Chennai. He has served as the chairman of Naval Research Board, DRDO, New Delhi from 2016 till 2021. Currently, he is a member of Board of Governors of National Institute of Ocean Technology, Chennai. In the past, he has been a member of the Technical Committee of Indian Register of Shipping, Mumbai, and a member of the Indian Technical Committee of Class NK, Japan. He has been associated with the design and construction of coastal research vessels for NIOT, passenger vessels for Andaman Islands, design of a feeder container vessel, and marine engineering laboratories in Indian marine engineering colleges. He has written 2 books as single author, Design Principles of Ships and Maritime Structures, and Glorious Water Transport Heritage of Kalinga, Ancient to Recent Times. He has obtained the Distinguished Alumnus Award 2021 of IIT Kharagpur. He has also been conferred the Eminent Engineer Award of the Institution of Engineers, India in December 2022. He is the founder president of the Technical Society Forum for River and Ocean Technology, or the acronym is FROST. And today's his the topic of his talk is Maritime Environment and Society. I am very privileged to mention the audience that he was kind enough in visiting my office, and I had his book, Glorious Water Transport Heritage of Kalinga, Ancient to Recent Times, and he was also a distinguished speaker in the Dhara conference, the Samudra Manthan, which he organized last year during Bali Yatra. With these words, I welcome you, sir, again to this distinguished series of lectures, and we are very happy to tell that you will have 40 to 45 minutes, then we will have a 10 to 15 minutes interaction time, and the audience consists of students, international students, faculties, and common people. With these words, again I welcome on behalf of the university, sir. Now the platform is all yours. Thank you, sir.
Good evening and namaskar, Professor Nachiketa Sharma and distinguished audience. It's a privilege to be here in this platform to speak to you on oceans and their connections with the human society. When Professor Sharma approached me, I was delighted to know that the Shiksha and Anusandhan University is going to start a integrated maritime studies center, and I immediately agreed that I could talk to you about oceans and their relationship with human society. Now, oceans is this topic is very big. So what I'll do is I have thought that I'll just brush the surface only and try to cover the entire gamut of what is the interaction between oceans and society. I hope you will excuse me for uh, uh, going over certain areas rather quickly, but we could come to them during the question and answer session. I would like to share my slides with you. PPT. Leave it like this. Yeah. Yeah. Yeah.
Yes.
Is it
Now it is visible. Yes, now it is visible.
when we talk of maritime environment, it's really a very big environment. Perhaps most of you are aware that about 2/3 of the surface of the earth is covered by oceans. Okay, if we look at the surface oceans in the world, there are, as you know, there are 5 oceans. Southern Ocean area being the most recent one, and these 5 oceans constitute about 65.7% of the total area of the surface of the earth, and land area consists of only about 29.1%. So the remaining 5% or so area is covered by salt water and fresh water, that is beyond the oceans, that is limited by the land area. And of that, only 2.2% total water area, only 2.2% is fresh water, most of which is blocked in glaciers and groundwater. So we have very little water in the rivers as fresh water. However, therefore, the oceans constitute a major portion of our surface, and we have to, yeah. Now, if you look at the surface of the earth, the southern part of the earth is mostly oceans with 2 continents there. One is Australia and the other is the Antarctic continent, which is in the South Pole, which covers the South Pole. And South Pole is not covered by water, it's covered by land. Whereas the northern part of the hemisphere is covered mostly by land, and the North Pole, however, is covered by water only, and there is no land on the North Pole. This is peculiar, but this is how our Earth is. And if you look at the surface of the Earth, the land surface is an average, consists of an average height of about 743 meters from the mean sea level, whereas the average depth of ocean is 3,734 meters below the Earth's surface, as we know it. That is the mean sea level. The highest point on the land is, of course, the Mount Everest, which is 8,850 meters, whereas on the land side, on the ocean side, the lowest point is the Marianas Trench, a trench with a portion called Challenges Deep, which is 10,800 meters deep. So you see, if from this diagram a very interesting fact emerges. If you had the Earth as a complete surface, a sphere, a smooth sphere, then the Earth would be covered entirely by water, and the height of which will be roughly the difference between the mean levels of the land and water. That would be a little more than 3,000 meters. So if the Earth was a full sphere, then we would all be immersed in water of about 3 kilometers deep. Now, if you look at the geography of the oceans, you will find that there are many areas where the oceans are very narrow and they provide ways to go from one side of the Earth to another side through something called straits. I have shown you a few straits here, which are important straits in the world's maritime activity area. You can see here Strait of Gibraltar, which separates the African continent from the Europe on the western side. You have the Strait of Hormuz, which separates United Arab Emirates from Iran. You have here Bering Strait. It's a very interesting strait, which is a strait between Alaska of the United States and the Soviet Union. On the here, the Malacca Strait is the strait that goes between the Malaysian Peninsula and the Indonesian island, which provides a seaway from the Indian subcontinent to China and beyond through this strait to the eastern side. Now there are two man-made canals which have been maintained by different countries. One is the Suez Canal, of which most of you might have heard, the canal between Asia and Africa, and there is this Panama Canal between North America and South America, reducing the distance of travel across from the east coast of USA to west coast of USA by more than 8,000 kilometers. So as you can see, all the oceans are connected. Now, if you look at the ocean bottom, we have already said that the average height of the ocean bottom would be more than 3,000 kilometers, but the deepest areas of the ocean are 5,000 or 6,000 meters below the mean sea level, which is known as the abyssal plain. This line here shows the ocean bottom in general. Now, from here, from the abyssal plain, the landmass rises, which is known as the continental rise, and then it goes on further rising, which is known as continental slope here, and then we have the land coming out of the sea, which is known as the continental shelf. Continental shelf is the flat area from land going into the sea before it jumps into the continental slope and continental rise and the abyssal plain. So this is the geometry of the Earth's bottom, and within this abyssal plain you have these mountains going up and down. The sea surface is not smooth, and here you have a small island coming up. Islands come up like this, but also if there is no island also, there could be ridges and mountains below the sea bottom. So this plays a major role in our understanding of the ocean. This area is commonly known as coastal zone. That is, the continental shelf zone is normally known as the coastal zone of the ocean, and the abyssal plain area is known as the deep water zone. Now, properties of water. Most of us know some properties of water, but they affect us greatly. So I have just thought that I'll highlight some of these properties. Water is highly incompressible. Water cannot be compressed with pressure. High surface tension giving rise to capillary action. This plays a part in disbursement of oil sprayed on ocean surface. extremely large heat capacity. Ocean can retain the heat to a large extent, but has a low thermal conductivity. Largely opaque to electromagnetic energy and visible part of the spectrum. That is what we can transmit radar and electronic signals in on the surface of the earth. We cannot do it in ocean because ocean water is opaque to electromagnetic energy. Therefore, electromagnetic transmission cannot be done. And say for same reason, it is also opaque to electromagnetic energy in the visible part of that is optical energy, and ocean bottom is dark. We'll look at this again. Extremely transparent to acoustic energy. This is something which should interest us. That it is transparent to acoustic energy, but opaque to electromagnetic energy. So radar and satellite communication below the water is difficult, whereas we could communicate below the water through acoustic energy. This is a very important point because if we want to do anything inside water, not on the surface, but inside water, then it is necessary for us to understand the acoustic behavior of the water. Now, freshwater density. Water behaves like normal fluid, expanding when heated and contracting when cooled below 4 degrees centigrade. So between 100 degrees and 4 degrees, if you increase the temperature, then the water becomes lighter. If you decrease the temperature, water becomes heavier. But water has this peculiar property that between 4 degrees to 0 degrees, it expands. It doesn't contract anymore, it expands. So if you go on cooling water, below 4 degrees, it would expand, and 4 degrees, it should freeze. And the density of water at that density of water or ice at 0 degrees is about 9% less than that of water. Therefore, you will find the ice floating in water. This is a property which is very important for us to understand the water behavior, particularly in the temperate climate. Temperature of the ocean. The sun hits the surface layer of the ocean, heating the ocean up. As we know, wind and waves mix the top layer of ocean. So this temperature circulates in the top 100 meters of the water. It gets mixed up. After that, we have seen water has low conductivity of heat. Therefore, it doesn't go down. So there is a range in which the temperature falls drastically, and then it remains more or less constant from 1000 meters to 4000, 5000 meters. It remains roughly at the 4 degrees centigrade. Now, salinity. The average ocean salinity is 35 ppt, that is 35 grams per 1000 grams of water. This number varies between 30 to 37, though average I have given is 35. Now, this salinity I am talking of is in deep ocean. When you come to rivers, there is no salinity, it is fresh water, and the ppt of being less than 5 is considered as fresh water. But at river mouths and lakes like Chilka, where seawater and fresh water keep mixing, the salinity reduces to something like 17. It's between 15 to 18 actually. So average you can take as 17 ppt. It is called brackish water. We have talked about density already. So density again in 3 zones. Top is mixed zone, as I have discussed. Bottom is deep zone, and the middle zone, where the temperature also varies, is called the intermediate zone, called the transition zone or pycnocline of the ocean. Now these 2 graphs give you the description of the temperature. First, we will look at this temperature graph on the right hand side. You can see this is the mixed zone about 100 meters, where the temperature remains as that of surface temperature. Absorption of heat keeps getting mixed up in this area, and temperature remains constant. But beyond this, the temperature falls sharply to about 1000 meters or 1 kilometer deep. That is between 100 meters and 1000 meters, the water keeps losing its heat, and the temperature comes to around 4 degrees, dropping only slowly to the bottom to 4 degrees. If it cools further, water would form ice. Similarly, similar to this, you can see the density rises at a sharp rate till about 1000 meters, and beyond that it remains constant. So you can see from this graph, on an average, ocean surface water density is 1.025, but at the bottom it goes up to 1.028. So this is the density property of water. Now freezing of seawater, I will not go through this. I have already discussed this. As the seawater becomes cooler at the bottom 4 degrees or below that, then the water becomes lighter and starts rising. When it starts rising, it starts shedding the salt content of water. So it becomes slowly fresh, and by the time it comes up, it is fresh water and it forms ice if the temperature goes below 0 degrees. So the ice floats, and below ice what we have? We have water of high salinity because it has shedded its salt. So we have a high salinity water below the ice level, and a very low salinity at the bottom, that is about 35 to 37 ppt. But at top, just below the ice, it may be something like 40. So this gives rise to a vertical circulation of water, that is at 40 degrees at a high salinity of top water becoming heavy, it keeps going down, and the bottom water comes up. I hope you understand this. Then we have another very interesting effect of the Earth, which is called the Coriolis effect. This Coriolis effect is something which you can understand very well. Earth moves in a circle, and therefore its circular velocity is constant, omega, that is constant. But its linear velocity varies. It is highest at the equator because of the large radius of the Earth at that point, and zero at the top, at the poles. In between, the water density varies, as is shown here crudely. That is 1,000 miles per hour at the equator, 800 miles per hour at 30 degrees, 500 mph 60 degrees axis, and zero at the pole. So what happens is that the atmosphere that is moving along with the Earth, it doesn't move. You can imagine if we move a plane giving only a vertical velocity, then it will automatically take that 1000 mph transverse velocity when it is at the equator, but it will experience only 800 mph transverse velocity when it is at 30 degrees axis. So at that point, the plane will experience a force pushing it to the left. So that force, that effect is called the Coriolis effect, which is instrumental in causing the atmosphere to blow at different velocities at different heights. And that gives rise to climate. We will not discuss much on this. We'll just pass through it. As I mentioned, we are only glancing through the various properties of water. Then water circulates. It transports latitudinal heat, that is the heat. You see, the Earth gets maximum heat at the equator because of its own inclination towards the sun, and minimum heat towards the poles. And that maximum heat heats up the equatorial waters, but it is not able to heat up the polar waters. But there has to be a heat budget. Therefore, 20% of lateral heat goes to lateral heat is only at the equator to poles. So the heat gets transported through atmosphere and gives rise to ocean currents, and influences weather and climate, and influences commerce. Then we have ocean circulation gives rise to currents of different types. Three basic types of currents: surface current, which is caused by the heat balance on the surface of water within 100 meters. Then you have deep water currents at the bottom where the water is absolutely zero at 4 degrees centigrade, and in between you have the bottom current is called the bottom water current is called the bottom current, and in between the surface and bottom we have a deep water. Causes of current are solar heating, wind, Coriolis effect, temperature gradient along the surface, and temperature gradient across the depth. This I have already mentioned to you, temperature gradient across the depth. Temperature gradient along the surface, you can understand that because of equator getting more heat, the temperature on the equatorial zone of water is roughly about 35 degrees centigrade. It's quite high. Whereas at the poles it is zero. And in between you have the temperate climate between 33 to 66 degrees latitude, which is called the temperate climate, and the water temperature is on an average 15 degrees. Of course, it's still varying. I'm just giving you the average values. So you have 0 degrees on top, you have 35 degrees in the bottom, and you have 15 degrees in the temperate climate. Same thing happens in the southern hemisphere. So this temperature gradient along the surface as well as along the depth, because of the movement of water due to change in salinity, gives rise to various currents. And there are many other reasons, but I have just listed a few reasons, main reasons. Then you have the other effect of surface waves that are created on the ocean surface. Surface waves, if you talk of a wave, generally we talk of a sine wave, whether it's electromagnetic or it's water waves. A simple transverse wave is represented through a sine curve called a regular wave. So water has a regular wave. Now when wind blows over water, wind is low velocity. Wind energy is transmitted to the water surface. So the top surface of the water starts getting small oscillations, generally at very low wind speed or no wind speed. The small oscillations that you have are called ripples. But as the wind increases, you get choppy seas, the wave height slowly increases, and it's also, if it still goes on in this thing, then it breaks. Now, why does a wave break? I can point out to you this shallow water effect. No, this we'll look at later. If normally the wave slope, that is wave height to wave length ratio, if it falls below 1:7, then a wave cannot retain itself in a wavy form, and the top wave peak breaks into water. That's how you get the foams. So you get choppy seas as the wind increases, and if the wind increases further and it over a long stretch of water and over a long period, three things are important: wind velocity, stretch of water, that is spread it is normally called, and the time over which the wind blows. It gives rise to what is known as a steady sea. So at the initial stages of steady sea, we have small wave heights and the waves keep breaking, and we have choppy sea. But if you have large wave, large amount of energy is transmitted in water, water takes on a smooth shape with a higher amplitude. And such waves with large wavelength, but higher amplitude and large wavelength, they are called swells. They are generally generated in mid seas. And swells have large energy, high energy content. If you know something about waves, you will know that wave energy is proportional to its amplitude square. So when you have a large wave, it travels over thousands of kilometers or miles without breaking, because there is nothing to absorb the energy. The energy just keeps getting transported. The viscosity of water does not affect the surface waves. That's why they are called gravity waves. So swells travel over long distance. It doesn't, because of the large wavelength and it doesn't affect surface shifts. But it affects when it comes to the shore because the swells have to break. So now if there is no swell but we have what is known as energies of irregular waves, as I mentioned before, when the wind energy is not really very large or this thing, then you have what we call irregular waves. And irregular waves are, you can understand, because you are engineering students, you can understand that irregular waves consist of a number of regular waves. And if you plot the energy spectrum, that is the frequency versus the amplitude square, then you get a curve of distribution of energy with various wave frequencies, and such a curve is called an energy spectrum. You can see here that as the sea becomes choppy, the energy spectrum gets distributed over a large number of waves, large number of frequencies. But from here to here, if you know, the major frequency here is here, this one, whereas at a lower frequency, one of the lower curves, the frequency is more and it gives rise to irregular waves. Now, if this happens when the waves are unidirectional, that is, wind is blowing in one direction. But if you have wind blowing in different directions, what you have is the energy spectrum is also spread in the 3 dimensions, that not only in the direction of the, since the direction itself is oscillating, then it's also such a sea is called confused. Now, when water comes to shallow water, because of the depth reduction, the water waves become steeper, and therefore, as it approaches a beach, the waves become steeper and steeper and steeper, and at the beach they break. So at all the beaches you will find that the wave is breaking and you have the sound, the energy is dissipated in the form of sound and light and viscosity. Storm surges are high winds of the coast and travel at a high wash the coast, drown certain areas of coastal areas. Type of wave that occur because of small oscillations of the tectonic plates below the sea surface. The Earth's tectonic plates below the sea surface. Small oscillations. As you know, the tectonic plate oscillations give rise to earthquakes. Tsunamis are caused in a way due to movement of tectonic plates, which may happen in land area, which is called earthquake. If it happens in tectonic plate movement happens in sea, then it gives rise to a large wave. That energy is transmitted to the water column, and there is a large wave generation which moves very fast, and it can only be dissipated when it reaches the sea. Such a tsunami is called, such a wave is called a tsunami wave. And like all waves, the tsunami wave doesn't die down in one go. It is followed by number of waves. So you have number of effects on the shore, not in one time, but over a period of time. So I have already discussed this. I just wanted to give you this view that the water particles on a wave surface move in circles. They don't move. Water particles do not move. It's only the energy that moves. Water particle moves in circles. If you put a floating object here and leave it without any force, then that object would move along this, but not the water particle. Water particles move in circles, and this circle, the wave nature is such that its circular effect dies down exponentially as it goes down. So therefore, you don't have any wave effect on the bottom of the sea, below a few meters of the sea. So the top layer only is affected by the wavy surface. This is very important for us to understand, because all artifacts that we design on the surface would be designed for waves, whereas all artifacts for underwater operation will not be affected by waves. And if you take a point measurement of the sea surface may look like this. either with respect to time or with respect to space. Such a sea is called a random sea. We have just discussed before that random sea is consisting of a number of sinusoidal waves or regular waves, and that can be represented by the energy spectrum. This is the view of a swell. You can see the energy moves continuously before it comes to shore and breaks. Or you can see the wave traveling across the ocean. And this is how the wave breaks. And this is tsunami. I hope you can see it. You can see as it comes to the shore, the depth reduces. The tsunami wave itself is high wave amplitude. It becomes very high and it comes like a wall to the shore and destroys everything on its path as the energy gets dissipated. Okay, this is broadly what I thought is the properties of water that should be told to you. Now we look at the other aspects of ocean, how it affects our society. I have already mentioned to you the continental shelf. This is roughly 2000 nautical miles, 200 nautical miles from the shoreline. Shoreline means the lowest low water level, that is during the tides, during the low tide, what is the water line from there. The demarcation is from there till 200 nautical miles would be the continental shelf. Of course, one can appreciate that these 200 kilometers, 200 nautical miles will not be accurate and it would vary from place to place. Based on these 200 nautical miles, the United Nations in 1984 formulated what is commonly known as law of the sea. That to whom does the sea belong? Does it belong to the nation that is next to it, or do the landlocked nations have any right over the sea? This was the discussion in 1984 by the heads of states of many countries, including India. And finally, the United Nations adopted what is now known as law of the sea. If you can see, this is the continental shelf exaggerated roughly. And this data that is given here is exact, but this is not exact. The continental shelf in some cases can go beyond, or some cases it can fall even below. So you can see here the first 12 kilometers, 12 nautical miles. 1 nautical mile is roughly 1.6 to 1.7 kilometers. This 12 nautical miles is what is called as territorial waters of the country to which the sea is attaching itself. So if you look at India, Indian coastline, 12 nautical miles all along the coastline will be our territorial waters. And territorial waters means we have a right to protect this water by our defense forces. Then we have what is called a contiguous zone, another 12 nautical miles, that is 24 miles from here, where we have the other activities of the nation, typically customs. Customs duties are imposed on items that cross this zone and come into Indian waters. And then from the sea reference line to 200 nautical miles is the what is known as exclusive economic zone, or EEZ. So this is the zone in which India has the exclusive right of our EEZ. India has the exclusive right to exploit this water for economic activities, but it cannot stop any other country entering into this zone. They will not have any economic rights, but they have a right of entrance and movement. And this is roughly, UN has identified that this should be the end of the continental shelf, which is not exactly correct. Sorry for this. Okay, look at this Indian landmass. If you look at the Indian landmass, has a EEZ starting from here at the extreme end of India. From here to the Pakistan's EEZ. We have a EEZ which goes like this. You can see it goes in between India and Sri Lanka, where we don't have the 200 nautical miles of water. So it is in between the India and Sri Lanka. It goes like this. And look at this place here, Andaman Islands. So around Andaman Islands also we have a large amount of EEZ. Similarly around the Lakshadweep Islands, we have a large amount of EEZ. What does it mean? Whereas land area of India can be told to be 3.287 million square kilometers, area of territorial is 0.15 meters, but area of EZ including that of Andaman Islands is 2.305 million square kilometers, which is roughly 70% of the land area of our country. That means 70% of the land area of our country, which is in the EEZ, we can exploit for our economic purposes without harming the oceans and maintaining sustainability so that our future generation can do the exploitation when their time comes. This is very important to understand. This has been understood by United Nations, this has been understood by all countries, and it must be understood by everybody concerned so that we can protect our oceans. What happens beyond the EEZ? Beyond the EEZ, the ocean is for everybody. It is commonly known as common heritage of mankind or humankind. High seas are considered as common heritage of mankind. Wealth recovered from high seas are to be shared by all nations. This is what United Nations has decreed, that wealth recovered from high seas are to be shared by all nations. And that I have not written here, but sustainability, maintaining sustainability in high seas is also a responsibility of all nations. Then, before 1984, a number of countries and companies had invested a large amount of money in exploring the ocean depths and finding what is where. Those 8 countries in 1984, since they had already invested money, they were given what is today known as pioneer investor status, who have the exploration rights, and eight countries have been given this right with demarcated areas of ocean to explore. 8 countries are 8 entities are 4 countries: France, India, Japan, Russia. Not India. India is one of the pioneer investors. And there are 4 other multinational companies who have citizenships in Belgium, Canada, Germany, Italy, Japan, and Netherlands, the UK, and the USA. Area demarcated for India is the Central Indian Basin. I don't know whether you know what is Central Indian Basin. Roughly, it is south of the southern tip of India to the south, between Maldives Islands and the Madagascar Islands. That area is the Central Indian Basin, which has been given to India to explore. Exploitation is different. Exploitation of that wealth would be as per the UN demarcated method, but exploration rights have been given to India. Why should India spend money in exploring? Because obviously a large amount of wealth will be delegated to India. So that is the reason. Now we have a look at the ocean wealth. What does the ocean contain that we are so concerned about? Here I have shown you some ocean wealth types. You know most of it, but let us look at this, the mangroves. The mangroves are trees that grow in brackish waters. They have a big contribution to our society because they protect the ocean coast from inundation into the area. While we have mangroves in Odisha, yes, we have deep mangroves starting from Kendrapura area down to the Recipital area. We have mangroves. Of course, off and on, this mangrove has already been depleted, but mostly mangroves are there. Then we have marine animals, aquatic species. I have shown here a olive turtle, about which we have heard a lot. And then we have what we know as seaweeds. Seaweeds is a high protein. Seaweeds is a botanical growth, like mangroves. They are botanical growth, but they are high protein items, which is a favorite dish in the Japanese menu. And this dish, this high seaweeds also give rise to give a lot of medicinal properties and are used in preparation medicines. Here I have shown a coastline. I have shown for two reasons here. One is the coastal livelihood depends on sea. How does it depend? Not only seaweeds and mangroves, but fishes. I'll show you in the next slide. But the other reason why I have shown you is this, that unless the coast is protected, then the coast gets inundated. You can see the houses on the bank have already gone under the sea, and these houses would go in no time. So it is necessary for us to protect the coastal zone, to protect the human habitat. This is where we interact with the sea directly. Now we have here other ocean resources. You can see here the fishes, and here what are these? These are what is that? Okay, marine growth. Let me skipping, the name is skipping to me. Corals. These are the corals. These will grow and stay there as housing for other maritime growth. Now this is, as you might have seen, these country boats that are used for near shore fishing. To a large extent, the fishing boats go out in the morning and come back in the evening, catch a fish. And these are the mechanized trawlers. You can see these items. These items are called davits. They are used to lower the boat and lift the boat with the fish in it. We'll go a little faster, perhaps. Then we have the other ocean wealth is oil and natural gas, the fossil fuels, which we are talking so much against today. But they have given us energy for the last 60 to 70 years, and perhaps they will give energy to us for the next 50 years. You can see the artifacts that are used to extract the oil from bottom of the sea, about 12 kilometers below the sea level. And you can see here, this is a fixed offshore platform where the legs are there and the platform is on top. This is a floating offshore platform. This is called a twin hull vessel, submersible, semi-submersible vessel with 2 hulls and 6 pillars. And this is a platform which is above the sea. This provides buoyancy which is below the sea, and the pillars connect the top platform to the bottom buoyant chambers. And here at the middle is the drilling tower. You can see the drilling tower here. This here is the drilling tower. This is the deep water drilling. This is called a TLP, where you have legs which are not really metal or concrete legs, but steel tubes connected in such a manner there is a little buoyant force always keeping the vessel on top. And this is known as tension leg platform. The legs are always in tension. So this reduces the movement of the platform in the horizontal plane to a large extent. And you can see the ropes going down for drilling activity. These 3 legs are converted to single tubes. You can see here. This is a tube actually. This is a tube inside which the ropes are going, and this is also a tube under which the ropes are going. These are called spar platforms. Here we have what is called a floating production, storage and offloading platform. It produces, it stores, and it offloads to other platforms, and it produces from a number of wells. You can see here there are a number of wells here. There is a platform here, there is a platform here. They also provide oil here for storage. These 2 platforms are standalone platforms. They don't have the storage device. They provide the storage platform, storage space here. And these are the oil wells from where oil is produced by this platform itself and stored in the vessel. And this oil that is stored is drill is transferred to other vessels that carry the oil to the shore to production facility or for export. So this is called floating production storage and offshore platform, FPSO. This is what is known as a drilling ship. A drill ship is a ship that is housing the drill platform. This can go to deep water, this can drill in deep water, and this can move away to another side. This is a movable drilling platform. If it is a fixed platform, it cannot move. These platforms are floating platforms, but they can only move slightly. Moving a TLP is very difficult, but semi-sub platform can move to smaller distances. So they can be towed to a new site. This FPSO is one which connects a number of sites. Drill ship is one which can move from site to site easily by its own propulsive power. Then you have under the ocean mineral nodules. You must have heard about mineral nodules. These nodules are generated as nodules 1 centimeter to about 30-40 centimeter diameter nodules. They are spread over the ocean bottom and they are rich in manganese and iron. That is not of our concern. Our concern is the other material that is there, that is nickel, cobalt, copper, and molybdenum. These metals are necessary for the earth because land-based material, these materials are limited in land-based applications. So these are mined by what is called ocean mining activity. I take great pleasure in telling you that the National Institute of Ocean Technology has developed a crawler which can move under the ocean bottom, pick up these nodules, and they are developing a lifting system which will bring it to the surface with a ship. So this is being found in 5,000 meter water depth in the central Indian basin, about which I have talked just a minute before. Then you have what is known as cobalt crust. Cobalt is a very rare metal, as you know, on land-based mining. This cobalt is deposited on the sides of the mountain rises, the hills of the under the sea. And if we can locate this and extract this, this occurs between 400 to 4,000 meters water depth. If we can extract this, we really get good wealth. Then you have what is known as sulfides. These sulfides are generated when you have undersea vents, the volcanic activity, the volcanic lava that comes out under the sea but above the ocean trench, ocean hills, ocean volcanoes, and they come down and then get deposited under this. These ocean sulfides are also rich in nickel, cobalt, and copper. So this is another area which requires our attention for extrapolation. Then in India, in coasts of Odisha as well as Kerala coast, we have the rare earth company, a government undertaking, extracts rare earth material from the shore as well as near sea areas from the sand, and which is basically uranium rich. So these are the wealths the ocean has. Then we have ocean energy. Ocean is full of energy. You can see windmills housed in ocean, and this is perhaps, I don't know exactly, perhaps a floating ocean windmill. Why are windmills installed at sea? Two reasons. One, the wind velocity is normally high at sea, and when it reaches the shore, it reduces. So you get large energy. Second reason is you get a continuous source of energy, unlike land where the wind energy varies, it fluctuates quite a lot. So you can have fixed wind energy platforms, so you can have floating platforms, but the energy requires to be transported to sea, to the shore through cables. That limits the distance to which you can install the wind energy platforms. Then you have what is called OTEC, Ocean Thermal Energy Conversion System. This is an NIOT design for OTEC vessel, which has two components to it. We'll look at it a little later. Enough to say, we have already seen the temperature variation in the ocean depth. That is, at the surface it is 30 to 35 degrees, and at about 1,000 meters it comes to about 8 degrees. So there is a large, about 20 degrees centigrade temperature difference along the ocean surface. So if the ocean depth. So if you can access this temperature, the heat content in the water column, then we can do miracles. We can absorb this energy. This is normally used, water evaporation or the reverse osmosis process through which we generate fresh water, and we can generate electricity through ammonia condensation. The other ocean thermal energy conversion platforms. This is the wave energy, where you can see that the waves come, there is a beach here, or there is an arm here through which the wave enters the platform, and there is a propeller here which moves in single direction, whether the waves are coming or going, reflecting back. They move in single direction and generate energy. That is the simplest form of wave energy we have. We have many other complicated forms. We'll look at it later. Then what you have here is tidal energy. We have talked about, I don't know whether I talked about tides or not. That's a very interesting phenomenon. So we have tidal energy which varies 3 to 4 meters of water level variation at river mouths. If you can harvest this height of water difference, potential energy of the tides, then we can generate this. This is a tidal energy generation platform. This is the high tide, this is the low tide. You can see the wave is coming here high, this is low, water enters in a cylindrical structure and moves the platform through the normal conventional ocean conversion systems. Oh my God. Okay, desalination. I can skip this. Let's go to some of these. Professor Sharma, can I take 10 more minutes?
Sir, I think if you can wind it up within 5 minutes, it will be okay, sir.
Okay. Okay. All right. Now we have transport. The main ocean support that humans have is transportation system. You can see a river boat. You can see a river boat carrying cargo. These are river boats. You can see the bank on the side, and these are river boats which are carried in a flotilla formation. That is small boats tied together and pushed by a tug. Then we have the small boats. You have seen the rubber dinghies used in flood relief. You see, this is a hydrofoil boat where the boat is above the water, and you have what is known as a planing boat. It skims the water surface. These are small boats used for various purposes. Now you have big ships. You have this very famous ship. You must be here seen this diagram number of times. Our own aircraft carrier, INS Vikrant, built by Cochin Shipyard Limited. This is a ro-ro vessel where vessel go in and get stored. The passengers stay on top. This is used as a ferry. And this is what is known as a container ship, the maximum transportation of containers, that is standard containers you see on Indian roads. They are moved from place to place with cargo inside. And this is a passenger vessel with a number of decks. You can see, I am showing you this to see the general look of each of these vessels. Then you have tankers, bulk carriers, you have tankers, and you have LNG carriers, liquefied natural gas in cryogenic condition. This is the most highly technically sophisticated vessel. Then you have ocean research, where you have coastal research vessels and ocean research vessels. We have also polar research vessels. These are scuba divers. You can see this. We have submarines, submersibles, AUVs, automatic underwater vehicles, and deep diving manned submersible Matsya 6000 being designed, and will be going down to 6,000 meters water depth in a year's time. And this India is probably the 6th or 7th country to have designed and sending a man down to the sea. If time permits later, through some questions, I can answer some things about this. Human activities damage water, there is air pollution, we know CFC, we know greenhouse gas emission from ships, and we have SOx, sulfur dioxide, sulfur oxide, and nitrous oxide emission causing acid rain. We have water pollution, we have ballast water discharge, acoustic pollution, noise produced by human activities affect the sea life, and pollution from human land-based activities, plastics, waste, garbage, industrial waste. So what should we do? I have narrowed down to 4 main areas. One is understanding the oceans. If we don't understand the oceans, we don't understand how to make it sustainable. Strict regulatory regime. There must be a strict regulatory regime asking people, asking operators, ship operators, offshore oil platform operators, anybody of industries dumping things to the sea to control their activity to sea damage. Then new technologies. New technology, very important. You know, you have heard about hydrogen and things like that. Okay. And all this requires innovation, supporting innovation to all these activities. I think that's all I have to tell you. Thank you very much. Thank you.
Thank you, sir. Thank you very much. Actually, each slide will be a full topic. So
Yeah.
I think I will take the liberty of just summarizing as quickly as possible the beautifully structured talk of Professor Suresh Mishra. Actually, he very nicely highlighted that the deepest portion is 10,900 meter and the highest point is 8,850 meters. So the difference, if you can put the entire water on the surface of the spherical earth surface, then the water will accumulate up to a height of 2 kilometers, the difference. And the latitude, the cold, the how the Persian Gulf is hot and the polar regions is cold, and very nicely he explained the different properties of water. The water's anomalous expansion has always mesmerized me, because you see the ice floats at 0 degrees centigrade and the water at 4 degrees centigrade lies below. So nature is so kind in putting the marine living beings alive in a freezing temperature also. Then the brackish water says salinity 0.5 to 17 ppt, vertical circulation, Coriolis effect, how the relative velocity will be there between different latitudes. Then the importance of ocean circulation, surface waves. There was an extensive discussion on these points. Tsunamis, how small oscillations of tectonic plates under the sea surface will lead to tsunamis, and the counterpart will be earthquakes. And very nicely explained continental shelf. And as all of you know, because we have two judges who have already delivered talk on the international law of the sea, and for all the knowledge of the audience, let me tell you that there is a tribunal, international tribunal for the law of the sea in Hamburg, Germany, and there are 21 judges, and the Indian judge, Justice Neeru Chadha, is now the vice president of that tribunal. So that's a pride moment for all of us. Then the territorial waters, exclusive economic zones, and the common heritage of mankind, Indian landmass, all these pioneer investor status, biological resources, the different vessels, and so what not actually. And finally, just to maintain sustainability, we must focus on understanding oceans, then the strict regulatory regime, new technology, and encouraging innovation. So I was very aptly actually listening to his talk. So this is so kind and nice of you, sir. The professor that you are, and you are blessed with a very nice way of speaking English, and that in a structured manner. So that has fascinated me from the days of the Dhara conference that I heard you in Kotak, and I am hooked to you. So I am extremely thankful and grateful to you. We are running short of time. Still, I think if the audience can have any questions, if anybody is listening to him, maybe there will be one or two questions. So I think we'll take this. Thank you once again. Thank you very much, sir. Anybody, any question? Okay. So if you don't have any question, I think so. On behalf of the SOA outreach cell and the university, I am extremely grateful and thankful to Professor Suresh Mishra ji for this illuminating talk, and he has agreed to deliver this talk. So and he is in Bengaluru, and still he could find out time and he could enlighten us on different topics. So I will be waiting for his physically when he will be available to Bhubaneswar, so that we can have more interaction with him. Thank you, sir. Thank you very much.
Thank you. Thank you. It's my pleasure.
Thank you, sir. Thank you. The meeting is over.
Okay. Thank you. ମୋ ଲେକ୍ଚରଟା କ'ଣ SOAFAL ଷ୍ଟାଣ୍ଡାର୍ଡ ହେଲା କି ନାହିଁ? Yeah, that's a complete ocean engineering and oceanography subjects. ନାଇଁ ମୁଁ ପଚାରୁଥିଲି କେତେ what was the audience like? How many people attended? ସେଥିପାଇଁ ଟିକେ କମିଥିବେ ଆଉ ଆଣ୍ଡ ଓସେନ୍ ବିଷୟରେ ବି ଲୋକମାନେ ବେଶୀ ଇଣ୍ଟରେଷ୍ଟେଡ୍ ନୁହନ୍ତି ତ, so I thought I will cover the whole thing for students.